Okay, let's kick off this deep dive. You're here because you want a shortcut, right?
Hmm.
A direct route to truly understanding complex information without drowning in data. And that's exactly what we promise and deliver on the deep dive. Forget information overload. We're here to distill the most important, often surprising nuggets of knowledge just for you.
And today we're embarking on a pretty fascinating journey, I think, into the very heart of machine learning, our focus, how we meticulously build, rigorously evaluate, and then, really fine-tune linear regression models. And we're using them to predict something as tangible and relatable as house prices. It's a problem that seems simple on the surface, but as we'll definitely see, it reveals layers of complexity.
Exactly. And we've got a fantastic stack of source material guiding us, primarily drawing insights from the IIT Madras Machine Learning Practice Course. It gives us a hands-on, deeply practical look at how Sklearn APIs bring these theoretical concepts to life, our mission, to help you, our listener, grasp the essential steps, understand the potential pitfalls, and uncover those surprising insights into crafting truly high-performing predictive models. It's really about building intuition just as much as understanding the code itself. So every great machine learning journey, every grand predictive endeavor, it all starts with the data. Always. It's our canvas, our raw material. For this deep dive, that canvas is a renowned California housing data set. So set the stage. What exactly is this data telling us? What kind of picture does it paint?
Right. Well, this data set is a bona fide benchmark in the machine learning world. It's a real go-to for many learners and researchers. It offers aggregated information about various districts or, more specifically, block groups across California. We're talking about 20,640 individual instances, each representing one of these block groups. Each instance comes with 8 numerical attributes, and our ultimate target, what we're trying to predict, is the median house value within that block group. Now, what's unique and really important to remember is that these values are expressed in hundreds of thousands of dollars. So if you see a two-door, that actually translates to a median house value of $200,000. And quite conveniently for our starting point, there are no missing values in this data set, which, always makes for a much cleaner initial analysis.
That's a huge relief, honestly. No missing values means we bypass a whole category of pre-processing headaches right out of the gate. That's nice. But let's dig into those 8 attributes. What are they? Do they give us any immediate intuitive clues about what might heavily influence house prices in these California communities?
Absolutely, and they're quite intuitive, really. We have Med and C, that's the median income in the block group, a pretty obvious candidate for influencing house prices, right? Then there's house age, which is the median age of the houses in that block. We also have AVGROOMs, the average number of rooms per household, and its counterpart, AVD bedrooms, the average number of bedrooms per household. Next, population, which is simply the block group's population count. And AVD occupancy, detailing the average number of household members. How crowded are the houses, basically? Finally, to round out our geographical context, we have latitude and longitude, giving us the precise coordinates of each block group. Now, when we perform that crucial initial data exploration, starting with simple histograms of these features, well, we immediately uncovered some really interesting distributions. They tell us a lot about the data's inherent quirks. For instance, both Med and NC, the median income, and our target variable, the median house value, displayed what we call long-tail distributions. Imagine a graph where most values cluster in the middle or lower end, but then there's this long, thin tail stretching out to very high values. This means while most areas have average incomes or house prices, there are a few exclusive, very high value areas that significantly, pull the average up. And here's where it gets really interesting with the target variable. We noticed a distinct truncation at a value of 5. This means any median house value above $500,000 was simply capped, just set to 5. You could literally see this as a pronounced spike at the very end of the target distribution's histogram. It's like a hard ceiling. Now, this isn't a natural data pattern. It's almost certainly a data collection artifact. And it's a crucial nugget of knowledge because it tells us our model won't be able to predict above $500,000 accurately unless we somehow address this limitation.
That truncation is a fascinating detail. It's almost like the data collection system just ran out of room at the top end. So what else did your initial exploration reveal? Any other surprises or strong signals in there?
Definitely. We also observed that features like AVGROOMs, AVBedrooms, population, and AV occupancy showed surprisingly wide ranges. And their histograms hinted at the presence of potential outliers, some really extreme values. This wasn't just a hunch, it was confirmed when we dug into their descriptive statistics. We saw a significant disparity between the 75th percentile and the maximum values for these features. This kind of large gap is a classic red flag, indicating the presence of extreme values or outliers that could potentially skew our model's learning if we don't handle them carefully. But perhaps one of the most powerful initial insights came from looking at pair plots. These are visualizations that show the relationships between all possible pairs of features. They're really useful. What immediately jumped out, and frankly makes a lot of intuitive sense, was how strongly median income, med and C, and the geographic location, which is essentially the interplay between latitude and longitude, correlated with house prices. You could visually see clusters and trends forming right there on the plots. This is a powerful aha moment because it confirms our real-world intuition. Location, 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 and the economic prosperity of an area are often the strongest drivers in real estate values.
So when we put all this together, the long tails, the truncated target, those potential outliers, and these strong correlations with income and geography, what does this all mean for us as we start thinking about actually building our predictive models? These initial insights sound absolutely vital, almost like laying the strategic groundwork before you even draw up the blueprints.
They are vital.
Yeah.
Absolutely. These initial insights are our guiding stars. Knowing about long tails, the truncation, and potential outliers immediately tells us we might need models or pre-processing steps that are robust to these characteristics. For instance, maybe a model that's less sensitive to extreme values or transformations that can help normalize those skewed distributions. Without this upfront understanding, we might just pick a model that's totally ill-suited for the data's true nature. We'd be flying blind. And understanding which features, like median income and geographic location, already show strong correlations with the target helps us intuit what might be most important for our model to learn. It guides our initial hypotheses about what features to maybe emphasize, what kind of model complexity we might need down the line, and where to focus our efforts in, say, feature engineering. It's like a seasoned detective understanding the crime scene before even considering suspects. You gather the clues first.
All right, we've carefully examined our data canvas. We understand its texture, its bumps, its strong colors. Now, before we jump into building anything sophisticated, there's always that crucial first step in machine learning, setting a baseline. Why do machine learning experts always talk about baselines? It seems like a fundamental, almost non-negotiable step.
It's absolutely non-negotiable, you're right. A baseline model is crucial because it serves as your common sense prediction, your minimum acceptable performance bar. Think of it this way. If your sophisticated complex machine learning model, which you've poured hours of effort into building and tuning, can't perform significantly better than a simple common sense rule, well, then it's not truly adding value, is it? It tells you your fancy model isn't actually learning anything meaningful beyond what a simple guess could achieve. It helps us validate that all our subsequent efforts are genuinely worthwhile. Without a baseline, you might think your model is doing great, when in reality, it's barely better than, say, always predicting the average price.
So what's a practical example of such a baseline in Sklearn? How do you actually create one to set that performance bar?
A fantastic and often used starting point in Sklearn is the dummy regressor from the sklearn.dummy module. As its name implies, it's a simple model that makes predictions purely based on basic statistical properties of your training data. That's it. For example, you can tell it to always predict the mean of the training labels, or the median, or a specific quantile, or even just a constant value you specify. Our sources illustrate this beautifully, showing that using the mean strategy often results in the worst error, primarily because the mean is highly sensitive to extreme values or outliers in your data, like those high house prices we saw. In stark contrast, strategies like predicting the median or a specific quantile, like 0.55, which is quite close to the median for our California housing data, given its skewed distribution, well, those tend to perform significantly better. They provide a more robust baseline, especially when your data has those pesky outliers or skewed distributions we discussed earlier. It's a quick way to establish that common sense benchmark before we even think about more complex algorithms.
Okay, once we have that floor for performance established with our dummy baseline, how do we start building a more intelligent linear regression model? What are the core computational approaches Sklearn gives us for, actually fitting that line?
Right. In Sklearn, you primarily have two core ways to train a linear regression model. The first is through the normal equation. This is a direct, closed-form mathematical solution. It computes the optimal coefficients in one single calculation without any iterative guesswork. The Sklearn.linear model. Linear regression class is the implementation that uses this method. It's exact, very precise, and doesn't require iterative tuning or setting tricky parameters like learning rates. That's the upside. However, its Achilles heel is scalability. It can be computationally expensive and painfully slow for very large datasets, especially those with a huge number of features, because it involves inverting large matrices.
Okay, so direct but potentially slow for big data. What's the other way?
The second, and often more practical approach for larger datasets is iterative optimization. This typically uses algorithms like stochastic gradient descent or SGD, and this is where sklearn.linearmodel.sgd regressor comes into play. What's fascinating about SGD is that it's particularly well suited for truly massive data sets. We're talking tens of thousands or even millions of samples. Instead of calculating the perfect solution all at once, it updates the model weights incrementally after processing small batches of data, or sometimes even just individual samples. This incremental nature makes it incredibly memory efficient and highly scalable. And crucially, it offers a much greater degree of granular control over the optimization process through a rich set of hyperparameters, allowing for fine-tuning that the normal equation simply doesn't provide.
I keep hearing about pipelines in Sklearn whenever people talk about building robust models. They seem really central. How do they fit into this process, especially when we're talking about pre-processing steps, like scaling features, before we feed them into our linear regression models?
Pipelines are, and I don't think this is an exaggeration, one of Sklearn's most powerful and elegant features, honestly. They're essentially a way to chain multiple preprocessing steps, like transforming features or scaling them together with a final estimator, such as our linear regression or SGD regressor model. This is absolutely critical for several reasons. Firstly, it ensures that all preprocessing steps, for example, using a standard scaler to bring all features to a similar numerical scale, are consistently applied to both your training data and any unseen test or validation data. This consistency is paramount for preventing something called data leakage.
Right, I've heard of that.
Yeah, where information from your test set inadvertently leaks into the training phase, giving you an overly optimistic and basically false sense of your model's real-world performance. Pipelines prevent that. Secondly, it just makes your entire machine learning workflow much cleaner, far more reproducible, and significantly easier to manage and share. For linear regression, a common and highly recommended pipeline typically involves a standard scaler, which normalizes feature scales, preventing larger valued features from dominating the model's learning, followed by either linear regression or SGD regressor.
Okay, so with this basic setup, a pipeline that includes scaling and a standard linear regression model using the normal equation, how did our initial linear regression model perform compared to that dummy baseline? Did it show the significant improvement we hoped for right off the bat, or was there more to the story?
That's the million-dollar question, isn't it? How did step one pan out? We used a shuffle-split cross-validation strategy. That involved 10 different folds, setting aside 20% of the data as test examples in each fold, just to ensure we got a robust evaluation. Our initial pipeline, consisting of standard scalar and linear regression, yielded a mean absolute error, or MAE, of approximately 0.53 on the training set and about 0.527 on the test set.
Huh, 0.53. That sounds familiar.
Exactly. When we compare this directly to our dummy regressor baseline, which also had an MAE of around 0.53, well, you might scratch your head. Now, it's true that our linear regression model did show a noticeable improvement in the final comprehensive comparison on the true held-out test set later on. There, it achieved an MAE of 0.32 compared to the dummy regressor's 0.53. But these initial cross-validation numbers told a very clear story. Both the training and test errors were high and strikingly similar. This particular pattern, where both training and test errors are high and the gap between them is small, is a classic, undeniable sign of underfitting. It means our model, despite being a linear regression, was simply not complex enough. It couldn't capture the rich underlying patterns in the California housing dataset. It's like trying to fit a perfectly straight ruler to a very curvy, nuanced line drawn on a piece of paper. The model was just too simple for the job.
Okay, here's where it gets really interesting, I think. If our simple linear model is clearly underfitting, meaning it's too simplistic to capture the data's nuances, how do we give it a richer vocabulary? How do we make it more complex to better understand those nonlinear relationships we suspect are hiding in the data, especially after seeing those initial pair plots showing curved patterns?
Right, to address that underfitting, a common and incredibly powerful technique is to introduce polynomial features. Instead of just using the original features directly, we transform them. This means we include higher degree terms like a feature squared, x squared, or maybe cubed, x cubed. But equally important, we also generate crucial interaction terms. These are essentially multiplications of two different features together, like feature A times feature B. This transformation effectively creates new synthetic features that are nonlinear combinations of the originals. By doing this, our model, which is still fundamentally a linear model under the hood, suddenly gains the ability to learn and approximate those complex nonlinear relationships in the data. Sklearn.preprocessing. Polynomial features is the dedicated, elegant tool within Sklearn that handles this transformation seamlessly. It's like giving our model more dimensions, more ways to bend and curve its predictions.
So after giving our model this expanded vocabulary with polynomial features, what did this added complexity do for its performance? Did we see the expected improvement in fitting the data, or were there any new challenges, maybe signs of going too far?
The results were quite encouraging, actually. When we integrated polynomial features into our pipeline, specifically, we opted for a degree 2, meaning we generated all polynomial combinations up to the second degree, squares and two-way interactions. So our pipeline now looked like this. Polynomial features, standard scalar, a linear regression. The impact was immediate and positive. The mean absolute error significantly dropped to around 0.46 on the training set and 0.48 on the development set. That's the data we use for tuning.
Okay, that's a decent drop from 0.53.
Definitely. This was a clear signal that the polynomial transformation helped the model fit the data much better, capturing more of its inherent nonlinearity and moving us away from that problematic underfitting zone. We also briefly explored setting interactionally true within polynomial features. This only generates the cross-feature products, like AB, explicitly excluding the individual feature powers, like A2. Interestingly, this alternative yielded a slightly higher error of 0.47. It suggested that, for this specific data set at least, including all the polynomial features up to degree 2 was more beneficial than just the interaction terms alone. It shows that sometimes these seemingly small choices in how you engineer features can actually matter.
Adding complexity definitely helps fight underfitting, which is great. But we constantly hear this warning in machine learning that a model can become too complex. What happens then, and how do we prevent it from becoming, too clever for its own good and just memorizing the training data?
Indeed. While adding complexity is our friend in fighting underfitting, it's absolutely a double-edged sword. An overly complex model can swing to the other extreme, leading to overfitting. This is where the model learns the training data too well. It's almost like it's memorizing every single detail, including the noise and specific quirks of that particular training set, rather than truly understanding the underlying general patterns.
Right, it fails on new data.
Exactly. The dangerous consequence is a model that performs exceptionally well on the data it was trained on, but, crucially, performs poorly on unseen data. It doesn't generalize. To combat this, we arm ourselves with regularization techniques. Regularization works by adding a penalty term to the model's loss function during training. This penalty is typically proportional to the size of the model's coefficients, the weights it learns. By discouraging these coefficients from taking on excessively large values, regularization effectively forces the model to be simpler and more generalizable, thereby preventing it from becoming too specialized or overfitted to the training noise. The two main types we explored are ridge and lasso. First, ridge regression. You'll find this as sklearn.linearmodel.ridge. Ridge adds an L2 penalty to the loss function. This penalty is proportional to the square of the magnitude of the coefficients. The beautiful effect of this L2 penalty is that it gently shrinks the model's coefficients towards 0. They really go exactly to 0, but they become much smaller and more uniform. This shrinkage is key to preventing overfitting because it makes the model less sensitive to individual, potentially noisy data points and encourages it to rely more broadly on all features, leading to better generalization on new data. The strength of this regularization is controlled by a hyperparameter called alpha in Sklearn, sometimes called lambda in textbooks, but alpha in the code.
Got it.
When we incorporated ridge into our pipeline with a fixed alpha of 0.5, just as an example, the training MAE was about 0.48. This was slightly higher than the polynomial regression without regularization, which was 0.46, perfectly demonstrating the impact of the penalty. It deliberately trades off a slightly less perfect fit on the training data for the greater good of potentially better generalization later.
Okay, so ridge shrinks coefficients. What about lasso?
Then we have lasso regression, implemented in sklearn.linearmodel.lasso. This applies an L1 penalty. This penalty is proportional to the absolute value of the coefficients, not the square. Now, what's truly fascinating here, and one of lasso's most exciting properties, is that the L1 penalty has a unique power. It can actually drive some coefficients exactly to 0.
Completely 0.
Completely 0. Imagine a data set with dozens or even hundreds of features, many of which might be noisy or irrelevant. Lasso doesn't just shrink their influence, it can completely silence them, setting their corresponding coefficients to 0. This means Lasso inherently performs automatic feature selection. It identifies and effectively discards less important features for us.
Wow, that's powerful.
It really is. It simplifies the model and can significantly improve interpretability. However, our initial attempt using Lasso with the default or small alpha, like alpha 0.01, actually showed a higher error of 0.52. This clearly highlighted the critical need for proper tuning of this alpha parameter for Lasso. Without careful tuning, the regularization might be too strong, zeroing out important features, or too weak, not providing enough regularization. Getting alpha right is key for Lasso.
Okay, so Ridge shrinks, Lasso selects features.
Yeah.
What if we want a bit of both?
Great question. If you're looking for the best of both worlds, the combined benefits of both Ridge and Lasso, you can turn to ElasticNet. It's a clever convex combination of both L1 and L2 regularization, meaning it applies both penalties simultaneously. The balance between the L1 Lasso-like and L2 Ridge-like penalties is controlled by another hyperparameter, the L1 ratio. An L1 ratio of 0 means it's purely Ridge, all L2 penalty, while an L1 ratio of 1 means it's purely Lasso, all L1 penalty. Values in between give you a mix. This incredible flexibility allows for a fine-tuned balance between coefficient shrinkage from L2 and automatic feature selection from L1. What's neat is that this ElasticNet penalty is often implemented directly within SGD Regressor by simply setting its penalty parameter to ElasticNet and then tuning both alpha and L1 ratio.
What's fascinating here is the SGD regressor seems to pop up repeatedly as we discuss these different models and regularization techniques. It was mentioned as a scalable option for basic linear regression, and now we hear it integrates various regularization types directly. What makes it such a versatile and frequently used tool? It sounds almost like the Swiss Army knife of linear regression in Sclearn.
You've hit on its core strength, exactly. SGD Regressor truly is the workhorse for linear regression, especially when you're dealing with very large data sets. Its primary advantage comes from its use of stochastic gradient descent, which, as we mentioned, is an iterative optimization algorithm. Unlike the normal equation method that computes a direct, one-shot solution, SGD updates model weights incrementally after processing small mini batches of data or even just individual samples. This incremental approach is what makes it incredibly memory efficient and scalable. It can handle data sets that simply won't fit entirely into your computer's memory. Beyond just scalability, though, it offers an unparalleled amount of granular control over the optimization process itself, which is precisely why it's so versatile and powerful for fine-tuning performance and integrating things like regularization so easily.
You mentioned incredible control. That sounds like a lot of levers and dials to potentially play with. What are its key settings or hyperparameters that we really need to understand to get the most out of it? What should we be focusing on?
There are indeed many critical hyperparameters in SGD Regressor that allow you to fine-tune its behavior. Let's break down the main ones. First, you can choose the loss function. Squared error is the standard for linear regression, aiming to minimize the sum of squared differences. That's usually what you want. But you can also opt for Huber loss. This is a fantastic choice if your data has outliers. As it's designed to be more robust, it acts like squared error for small errors, but more like absolute error for large ones, making it less sensitive to those big mistakes caused by outliers.
Okay, loss function choice. What else?
Second, and this is where its versatility truly shines, it directly supports regularization. As we just discussed, you can apply L1 Lasso, L2 Ridge, or ElasticNet regularization simply by setting its penalty parameter. You then control the strength with the alpha parameter and, if using ElasticNet, the L1-L2 balance with L1 ratio. This integrated regularization is incredibly convenient.
Right, and the learning rate.
Third, and critically important for performance and convergence, is the learning rate strategy. This dictates how the model adjusts its step size during optimization, essentially how fast or slow it learns over time. You can set it to constant, optimal, which uses a theoretically optimal decay, in-scaling, the default where it decreases over time, or adaptive, which cuts the rate if progress stalls. Each strategy offers a different rhythm for how the learning rate decays or adjusts, profoundly impacting how quickly and effectively your model converges to a good solution.
That sounds crucial. Anything else major?
Fourth, SGD Regressor provides early stopping. This is a really powerful feature. It allows the training process to halt automatically when performance on a separate validation set stops improving significantly. It's like having a smart coach tell your model, okay, you're not getting any better on new stuff. Let's stop before you just start memorizing the training answers.
Prevents wasted time and overfitting.
Exactly. It prevents unnecessary computation and, crucially, helps prevent overfitting. You can control this with parameters like toll, the minimum required improvement threshold, night or no change, how many consecutive epochs without improvement before stopping, and validation fraction, the percentage of training data held out for this early stopping check. You can also explicitly set an upper limit on the number of training epochs using Maxiter. A useful empirical heuristic, a rule of thumb, is to set Maxiter to roughly seal 106 N samples. The idea is SGD often finds a good solution after effectively seeing about 1 million samples pass through. Lastly, and always recommended for reproducible results, you should set the random state parameter. And for general good practice in SGD, it's usually advised to set shuffle. True. This ensures the training data is shuffled before each epoch, preventing the model from getting stuck in patterns related to the original data order.
I remember hearing, maybe you mentioned it earlier, that SGD regressor is particularly sensitive to feature scaling. Why is that the case? Is it because of how it learns incrementally, piece by piece?
You're absolutely spot on. It's intrinsically linked to its incremental learning process. SGD regressor is highly sensitive to feature scaling. The core reason lies in how stochastic gradient descent updates the model's weights. It bases these updates on the gradients of the loss function with respect to each feature. Now, if your features have vastly different numerical scales, imagine one feature ranging from 0 to 1 and another from 0 to 100,000, the feature with the larger values will naturally produce much larger gradients. It just will. This means its updates will disproportionately dominate the optimization process. The model will spend way too much energy trying to adjust for the large-scale feature.
So it gets thrown off balance.
Exactly. It can cause very slow convergence or oscillations where the model bounces around the optimal solution or even getting stuck in a suboptimal spot altogether. This is precisely why using a standard scaler in a pipeline before SGD regressor is not just recommended, it's almost mandatory in practice. Standard scaler transforms each feature so that it has a mean of 0 and a standard deviation of 1. This brings all features to a similar scale, ensuring that each feature contributes more equally to the gradient updates. The result: faster, more stable, and ultimately more effective convergence for SGD regressor. It ensures every feature gets a fair say in guiding the model towards the best solution.
And what's the deal with these different learning rate strategies you mentioned? In scaling, constant, adaptive. They sound like they're absolutely key to getting SGD regressors to perform optimally. Could you walk us through a common scenario where one might clearly outperform the other? How do you choose?
Yeah, this is indeed where you really fine-tune the optimization process for SGD regressor. The learning rate determines the size of the step the model takes at each iteration as it descends the loss landscape towards the minimum error. The default strategy is in-scaling, inverse scaling. Think of it like a car slowing down as it carefully approaches its parking spot. It takes larger steps initially to quickly move towards the general area of the minimum, and then gradually smaller, more precise steps as it gets closer. This helps prevent overshooting the optimal solution. It's a generally robust default, often a good starting point. Next, there's the constant strategy. As its name implies, the learning rate remains fixed throughout the entire training process. This is simple conceptually, but it can be notoriously hard to tune effectively in practice. If the learning rate is too high, the model might just bounce around the optimal solution forever without ever settling down. If it's too low, convergence can be painfully slow, like trying to cross a continent 1 millimeter at a time. It's less flexible for complex loss landscapes. Then we have the adaptive strategy. This one is more dynamic and, well, adaptive. The learning rate stays constant as long as the training loss continues to decrease steadily. However, if the loss plateaus for a specified number of iterations, meaning the model isn't learning much new, it's kind of stuck, the learning rate is automatically reduced, typically by dividing it by 5, and training continues from there.
So it adjusts itself.
Exactly. This helps the model adapt to the loss landscape, automatically slowing down when it senses it's getting stuck or oscillating too much. Our demonstrations actually showed that an initial high itai, that's the initial learning rate value, with the default in-scaling strategy could lead to unstable learning curves with lots of oscillations. Reducing itai or choosing a more appropriate strategy, like adaptive, often makes the training loss decrease smoothly and monotonically, which is really the ideal behavior you want for stable and efficient convergence. It's about letting the model adjust its pace dynamically based on progress.
Fascinating how much control there is, really turning the learning process into an art form, or at least a careful craft. What about warm start and average SGD? They sound like they offer even more advanced ways to manage the training process or maybe diagnose issues.
They absolutely do, offering even more nuanced control and insight. Warm Start True is a neat trick. It allows the fit method of SGD regressor to continue training from where it left off in the previous call. By default, each time you call fit on a model, it reinitializes the weights and starts fresh. Kind of forgets everything. But with warm start true, if you call fit multiple times, it simply resumes training from its last learned state.
Oh, that's handy.
It's incredibly useful for monitoring the loss function iteration by iteration. You can train for just one epoch, record the loss, then call fit again for another epoch, and so on. This helps us diagnose convergence issues, visualize the learning process step by step, and effectively iterate on training without losing any progress made so far. It's like being able to pause your learning, check your notes, and then pick right up where you left off. Then there's averaged SGD, which you enable by setting average true or average integer. Stochastic gradient descent updates can sometimes be noisy, a bit jumpy, because they use very small batches of data. Each gradient estimate based on a small batch can be quite variable. Imagine trying to find the bottom of a valley by taking steps based on a slightly blurry, shaky map. You might wobble a bit on your way down. Averaged SGD helps to stabilize the weight updates by, quite literally, averaging the model's weights over previous iterations. If you set average true, it averages over all updates made during training. If you set average to an integer value, say average 10, it means averaging begins only after a specified number of samples or iterations have been seen. In this example, after 10 samples. Averaging kicks in later. This technique often works best empirically with a larger number of features and maybe a higher initial learning rate, eta, as the averaging helps to smooth out those noisy updates that can arise from large step sizes. It's a sophisticated method aimed at arriving at more stable and often more generalizable final weights, effectively cutting through the noise of the SGD process.
So what does this all mean in the end? We've explored our data, we've built these different models, we've even dabbled in making them more complex and then trying to make them more efficient with SGD. But how do we really know if they're any good? How do we evaluate their performance robustly, especially when we know that a single test score might not tell us the whole unbiased story?
This is such a crucial phase, you're right. It's often overlooked or rushed, but it's absolutely essential for building truly reliable machine learning models that you can trust. A single train test split, while a good initial sanity check, can easily give you an overly optimistic or sometimes an overly pessimistic view of your model's true performance. It's just one snapshot. The test set might, by sheer chance, be too small, or it might contain only the easiest examples, leading to an inflated sense of accuracy. Or maybe it contains all the hard cases. To get a robust, dependable estimate of generalization performance, that is, how well your model will perform on truly unseen data in the real world, we rely heavily on cross-validation. This technique repeatedly splits the data into different training and testing subsets, training and evaluating the model multiple times. This gives us a much more reliable average performance and crucially helps us understand its variability or consistency.
That makes perfect sense. A single test run is like judging a marathon runner based on just one quick sprint. It doesn't capture the whole picture. When we evaluate these regression models, what are the key metrics we should be looking at? I know Sklearn has a default score, the R2 score usually, but are there more nuanced ways to measure success beyond just that single number? What else tells the story?
Right. For those familiar with Sklearn, you know its default score. Method for regression models typically provides the R2 score, the coefficient of determination. And as a quick reminder, an R2 of 1.0 is perfect prediction. 0 means your model is no better than just guessing the average target value. And negative R2 means it's even worse than that. But beyond R2, Sklearn.metrics offers a rich toolkit of other key metrics that provide different, often complementary insights into your model's performance. You really want to look at several. Let's consider a few key ones. Mean absolute error, MAE, is the average of the absolute differences between your predictions and the actual values. It's often preferred because it's less sensitive to outliers than mean squared error. It doesn't square the errors, so large errors don't get disproportionately magnified. It tells you, on average, how far off your predictions are in the original units of your target variable.
So like dollars in our case.
Exactly, hundreds of thousands of dollars in our case. In contrast, mean squared error, MSE, does average the squared differences. This metric penalizes larger errors much more heavily, making it highly sensitive to outliers. Think of it. An error of 10 becomes 100 when squared, while an error of 2 only becomes 4. So MSE really screams if you have a few big mistakes. Useful if large errors are particularly bad for your application. Then there's mean squared log error, MSLE. This one's particularly useful for targets that have exponential growth characteristics, like maybe population figures or sales data over time. What's interesting about MSLE is that it tends to penalize underestimation more heavily than overestimation, which can be crucial in certain business contexts where missing a target might be considered worse than overshooting it slightly. We also have mean absolute percentage error, MAPE. This gives you an idea of the error as a percentage of the actual value, offering a relative sense of accuracy, which can be easier to interpret sometimes. Median absolute error, MEN-A, is a highly robust alternative to MAE because it computes the median of the absolute differences, making it almost entirely unaffected by extreme outliers. If you have crazy outliers, MED-E might be your friend. And finally, max error simply tells you the single worst-case error your model made on the test set. Though it's important to note this metric is only available for single output regression problems. A critical distinction to keep in mind when looking at all these in Sklearn, especially with cross-validation, is the difference between scores and errors. Scores are metrics where a higher value is always better, like R2. Errors are metrics where a lower value is better, like MAE or MSE.
Right, lower error is good.
Exactly. For consistency in things like grid search CV or cross-validate, where the goal is often to maximize a score, Sklearn often uses neg prefixes for error metrics. So you'll see things like neg mean absolute error. This converts the error, lower is better, into a score, higher is better, because it's negative. It just makes the optimization framework simpler because it can always aim to maximize the score.
That clarifies the metrics perfectly, especially the neg part. You mentioned cross-validation for robust evaluation. What does that actually involve in practice? How does it truly give us a more reliable, generalizable picture of our model's performance compared to just one split?
Cross-validation, at its core, involves repeatedly splitting your available data, usually your training data, into different training and test or validation sets. Then you train and evaluate your model multiple times, once for each split. Instead of just one snapshot of performance from a single train test split, this gives us many training and test error estimates from slightly different data subsets. This collection of estimates allows us to calculate not just an average performance, which is already more reliable, but also to understand the variability or standard deviation in our model's performance. This variability is crucial because it tells you how much your model's performance might fluctuate when exposed to different unseen data samples. It helps answer the question, how consistently will my model perform in the real world? Is it robust? Sklearn provides several common cross-validation iterators to facilitate these splits automatically. K-fold is a classic. It divides the data into K equal size folds, say 5 or 10. In each iteration, K1 folds are used for training, and the remaining single fold is held out for testing. This process repeats K times, ensuring every data point gets to be in a test set exactly once. It's systematic and thorough. Leave one out, LOOCV, is a special extreme case of K-fold where K equals the total number of samples, N. Each individual sample gets its turn as the test set, with the model trained on all N1 other samples. While exhaustive and providing very precise estimates of generalization error, it can be computationally incredibly expensive for large data sets, making it impractical in many real-world scenarios. Training in models is often too much.
Yeah, that sounds intense.
It is a highly flexible and robust option, and one our sources consistently used for its robust properties is shuffle split. This is a random permutation-based strategy. Instead of fixed contiguous folds like K-fold, it generates a user-defined number of independent train-test splits by first randomly shuffling the entire dataset and then splitting it into training and test sets based on specified proportions, or AIG, 80% train, 20% test. This makes it particularly robust to potential class distribution imbalances or ordering effects within your dataset, as the shuffling helps ensure that each split is a truly random representation of the overall data. Our sources typically employed shuffle split with maybe 10 splits and a 20% test size 0.2, providing a great balance of robustness and computational efficiency.
Okay, so cross-validation gives us a better average score and a sense of variability. Beyond just getting that average score, can we pull even more detailed insights from it? For instance, can we see how consistent the model is across different data portions, or maybe diagnose specific problems like whether it's learning too much from the training data or too little?
This raises an important question, and the answer is a resounding yes. This is where sklearn.modelselection.crossvalidate really shines. It's a powerhouse function, far more informative than the simpler cross-val score. Cross-validate provides a rich dictionary of results that goes way beyond just the single test score per fold. This dictionary typically includes fit time, the time taken to train the model in each fold, useful for understanding computational cost; score time, the time taken to evaluate the model in each fold; test score, the evaluation score, scores if you request multiple, on the test set for each fold. This gives you the distribution of performance. But crucially, if you set return train score true, it also returns the train score. This is the score calculated on the training portion within each fold.
Ah, so you can compare train and test within each fold.
Precisely. This train score is invaluable for diagnosing issues like underfitting or overfitting, because directly comparing training and test performance across the folds is absolutely key to understanding your model's learning behavior and its generalization gap. Optionally, cross-validate can even return the estimator object itself for each fold, allowing you to inspect the actual trained model objects if needed. And unlike cross-val score, cross-validate also allows you to specify multiple scoring metrics at once, like MAE and R2, giving you a truly comprehensive view of performance across different aspects in a single run.
That's incredibly helpful for comprehensive evaluation. But beyond just the numbers, even the train test scores, how do we visualize these concepts like underfitting or overfitting? Is there a diagnostic tool that provides a clear, intuitive picture of these issues, almost like an X-ray of our model's learning process as it sees more data?
Yes, absolutely. And this is where learning curves truly shine as that visual diagnostic X-ray for your model. Sklern.modelselection.learning curve is the dedicated tool for this. With learning curves, we plot the training error, or score, and the test error, or score, against the number of training samples used to train the model. So the x-axis isn't iterations, but rather increasing sizes of the training data set. For example, trained on 100 samples, 500 samples, 1,000 samples, etc. Now let's consider the diagnoses you can make from these plots. For underfitting, you'll typically see both the training error curve and the test error curve plateau at a relatively high error level. And importantly, the two curves will be quite close to each other. There won't be a big gap.
Both bad and close together.
Exactly. This is a classic, undeniable sign that the model is simply too simple. It fundamentally can't learn the inherent complexity of the data, even if you give it more and more examples. Adding more data won't help significantly here. The model itself needs to be made more complex, perhaps by adding those polynomial features we discussed earlier, or choosing a different model type. This is exactly what we saw with our initial basic linear model. Both errors were high and relatively close, pointing directly to its inherent simplicity being the core issue. Conversely, for overfitting, the learning curve looks quite different. You'll typically see the training error being very low, sometimes almost zero, especially as more training data is added. But the test error will be significantly higher, and there will be a large and persistent gap between the training error curve and the test error curve.
Low training error, high test error. Big gap. Got it.
That's your big red flag for overfitting. It means the model has effectively memorized the training data, including its noise and specific quirks, and isn't generalizing well to new unseen examples represented by the test set. In this scenario, providing more training data could potentially help close that gap by exposing the model to more diverse examples of the true underlying patterns, forcing it to generalize better. Alternatively, applying stronger regularization techniques could also help by simplifying the model and forcing it to generalize. The learning curve function can also optionally return fit times, which allows you to plot how the model training time scales with the size of the training data, offering another important diagnostic insight into the model's efficiency and scalability.
So we've identified that our initial linear model was underfitting, and adding polynomial features definitely helped improve things. But then we have all these extra settings that we introduce, like the degree for the polynomial features, or the alpha value in ridge, or lasso regularization. These are the hyperparameters, right? The knobs we set before training starts. How do we find the best values for them out of potentially dozens or even hundreds of possibilities? It sounds like a real needle in a haystack problem sometimes.
That's precisely where hyperparameter tuning comes in. And you're right, it's absolutely a critical, iterative part of the machine learning workflow. It's often where the real performance gains are found. Hyperparameters are exactly those parameters that are not learned from the data during the training process itself. Instead, they are set by us, the practitioners, before training begins. Examples include the degree for polynomial features, the alpha value controlling regularization strength in ridge or lasso, or the eta initial learning rate and learning rate schedule in SGD regressor. The list can get long. The entire goal of hyperparameter tuning is to systematically search for the specific combination of these hyperparameter values that yields the optimal model performance. And that performance is typically measured by robust cross-validation scores calculated on a dedicated validation dataset separate from the final test set. It's less about finding a single best model type and more about finding the optimal configuration for your chosen model architecture.
That makes sense. It's about tuning the settings for the best outcome. Is there a standard recommended process for how to split your data to perform this tuning effectively without biasing your final performance estimate? Because I imagine accidentally peeking at the final test data during tuning could lead to some pretty misleading results about how well the model will actually do in the wild.
Absolutely, and avoiding that data snooping bias, as you called it, is paramount for trustworthy results. The recommended data splitting strategy for proper tuning involves three distinct, completely isolated sets. First, the training set. This is the largest chunk of your data used to actually train the model with each different hyperparameter combination you want to test. This is where the core learning of patterns happens. Second, the validation set, sometimes called the development set. This data is held out completely separate from the training process within each tuning iteration. It is used only to evaluate the performance of each model trained with a different hyperparameter combination. It's how you compare the different settings and select the best combination, because it gives you an unbiased estimate of how well each configuration generalizes before you commit to your final choice. And third, the test set. This is a completely separate, pristine, unseen dataset that is ideally set aside from the very beginning of the project and used only once at the very, very end of the entire process.
Just one final check.
Exactly. Its sole purpose is to report the final, true, unbiased performance of the chosen, best-tuned model on truly unseen data. This is your ultimate report card to the world. This strict separation prevents you from inadvertently tuning your hyperparameters based on the test set's specific characteristics, which would lead to an overly optimistic and ultimately unreliable performance estimate. So the overall process is iterative and disciplined. For each hyperparameter combination you want to explore, you, or an automated tool, train a model on the training set, then evaluate its performance using cross-validation within the training set or on the separate validation set. After evaluating all combinations, you select the model configuration that achieved the best score on the validation metrics. Finally, you typically retrain this identified best model configuration on the combined training and validation data to leverage as much data as possible for its final training. And then, and only then, you perform a final definitive evaluation on the isolated, untouched test set to get your trustworthy performance measure.
That rigorous three-way split makes a lot of sense for maintaining integrity. But manually testing every possible combination sounds incredibly daunting, especially if you have several hyperparameters, each with a wide range of potential values. The number of combinations could explode. Are there automated ways to search for these best hyperparameters, tools that can handle this search systematically?
Yes. Fortunately, Sklern provides powerful and automated tools for this, saving us from that potentially massive manual exhaustive process. The first main one is Grid Search CV. Think of it like a chef meticulously trying every single ingredient combination from a predefined menu. Polynomial degree 2 with alpha point 1. Degree 2 with alpha point 5, degree 3 with alpha point 1. It exhaustively searches through all possible combinations of hyperparameter values that you explicitly specify in a grid. You define the grid of possibilities. It's thorough. It guarantees finding the absolute best combination within that exact defined grid. But as you suspected, if your pantry of options, your grid is massive, it can become computationally very expensive and take a long time to run. For example, our sources showed how it was used effectively to tune both the polynomial degree, trying values like 1, 2, 3, and the alpha for ridge or lasso regularization, trying maybe 20 different alpha values logarithmically spaced in a specified range simultaneously.
Okay, grid search is exhaustive but potentially slow. What's the alternative if the search space is huge?
The second major tool, often more efficient for larger search spaces, is randomized search CV. Instead of checking every single combination like grid search, randomized search CV samples a fixed number of candidate combinations from specified probability distributions or lists for each hyperparameter. You set a computational budget using the niter parameter, which determines how many different random combinations it will try. Let's say you set niter 50, it will try 50 random combos, regardless of how many total theoretical combinations exist.
So you control the time it takes.
Exactly. This is a significant advantage as it allows you to choose how much time or computational resource you want to spend tuning, largely independent of the total number of parameters or their possible values. It's like that same chef trying random but hopefully smart combinations based on their experience. Let's try degree 2 with a random alpha around 0.01 and maybe try SGD with an adaptive learning rate. You're effectively trading off exhaustive certainty for much greater efficiency, often finding very good, if not the absolute best, solutions much faster. A practical tip for both grid search CV and randomized search CV is that they can often be run in parallel to speed up the process significantly. You just use the njobs1 parameter, which tells Sklern to utilize all available CPU cores on your machine. Also, setting error score 0 or error score np.nan can be very useful. This tells the search what score to assign if a particular combination of hyperparameters leads to an error during model fitting, which can happen. This prevents the entire search from crashing and allows it to continue evaluating other combinations, simply recording a poor score for the problematic ones.
That's brilliant. Parallel processing and error handling make these tools much more practical. So beyond these general search tools, are there any specialized tools optimized for tuning specific models, like maybe those regularization models we discussed earlier?
Yes, there are, and they can be incredibly efficient for their specific task. For regularization specifically, Sklern offers specialized estimators like Lasso CV, Ridge CV, and Elastic Net CV. These estimators are incredibly useful because they have built-in cross-validation capabilities and are optimized internally to efficiently find the optimal alpha, the regularization strength parameter, for their respective models across a predefined range of values. This is typically much more efficient than using a general grid search CV if you're only trying to tune the alpha parameter for these specific types of models. They leverage internal algorithms, like coordinate descent paths, that exploit the structure of the regularization problem to speed up the search for the best alpha significantly. They're designed for speed and convenience in that specific hyperparameter tuning niche.
And finally, how can we visualize the effect of tuning just a single hyperparameter? Say, if I'm trying to decide the best polynomial degree, or the ideal initial learning rate for SGD. Is there a way to see how performance changes as that one setting is varied, giving me a more intuitive understanding of its impact beyond just the final number from grid search?
Yes, this is where validation curves truly shine as another excellent diagnostic and visualization tool. Using sklern.modelselection.validation curve, we can plot the training score and the validation score, calculated via cross-validation, as a function of a single hyperparameter's value across a range you specify. It provides a clear visual diagnosis of how that specific parameter impacts both model fit, training score, and generalization ability, validation score. It's like being able to smoothly turn a single mob and see exactly how the training and validation performance respond on a graph. For example, our sources showed a compelling validation curve where they plotted the error, or score, against polynomial degrees ranging from 1 through 5. They observed a very clear and instructive pattern. The validation error was lowest specifically at degree 2. Beyond that point, as the polynomial degree increased further to 3, 4, 5, the validation error started to increase again, while the training error continued to drop or stay very low.
Classic overfitting signature again.
Exactly. This is a classic visual indicator of overfitting at higher degrees. The model gets too complex, starts to memorize the training data's noise, and loses its ability to generalize to new unseen data represented by the validation score. This curve visually confirmed degree 2 as the optimal choice for polynomial features in this context, clearly showing that sweet spot between underfitting at degree 1 and overfitting at degrees 3+. Another compelling example they showed was a validation curve for turning eta, the initial learning rate, for SGD regressor. They saw that if eta was too low, the errors were high because the model was learning too slowly, maybe not even converging properly. Conversely, if ATAT was too high, it also caused errors to shoot up, indicating that the model was likely overshooting the optimal solution with huge erratic steps becoming unstable. The curve clearly indicated an optimal range for ATA where both training and validation errors were lowest and, importantly, showed low standard deviation across the cross-validation folds, indicating stable performance. Validation curves are invaluable. They help us pinpoint these optimal points or ranges visually, allowing us to consider not just the raw average performance, but also the stability and the risk of overfitting associated with different hyperparameter values. They really give you that critical intuition about your model's sensitivity to its settings.
Okay, after all this deep diving, from understanding the quirks and surprises in our data, building those essential baselines, exploring different, more complex models like polynomial and regularized ones, mastering the versatile SGD regressor, and then going through rigorous evaluation and meticulous tuning. Which model actually emerged as the champion for predicting California housing prices in this specific analysis? What did we learn from the final comprehensive comparison on that ultimate untouched test data set?
This raises the crucial question, right? And the answer absolutely must come from that final conclusive comparison performed on the completely held out true test set. As we discussed, this is the data that the models have never, ever seen before, not during training, not during validation, not during tuning. This ensures we get the most reliable, unbiased estimate of how our models will truly perform on future unseen data in the real world. We evaluated all the final, tuned models using mean absolute error, MAE, where, remember, lower is always better. So let's recap the results. We started with our baseline. The simple dummy regressor gave us an MAE of approximately 0.53. This was our common sense bar, the score to beat. Our initial linear regression model using the normal equation and proper scaling showed a significant improvement, bringing the MAE down considerably to 0.32. A clear step forward from just guessing the median.
Much better already.
Definitely. Moving to iterative optimization, the SGD regressor, after its hyperparameters were carefully tuned using randomized search CV, achieved a slightly better MAE still, coming in at 0.31. This proved the value of its tunability and flexibility for squeezing out a bit more performance. Then came the nonlinearity. Introducing polynomial regression, specifically degree 2, tune, significantly improved performance, bringing the MAE down further to 0.28. This was a big jump, confirming that capturing those nonlinear relationships was indeed key in modeling this housing data effectively.
Okay, 0.28 is looking pretty good.
Getting there. Then, when lasso regression was properly tuned, which involved finding an optimal alpha and potentially a different polynomial degree, our sources found degree 3 worked well with lasso in its optimal configuration. It also achieved an MAE of 0.28. It performed on par with the general polynomial regression model, demonstrating that its automatic feature selection power could deliver comparable results while potentially simplifying the model. But the top performer in our comparison, the winner after careful tuning using grid search CV, which, for instance, might have confirmed degree 2 for polynomials and found a very specific optimal alpha, like 0.0078 for regularization strength, was ridge regression. It delivered the best performance overall in this specific analysis with an impressive MAE of 0.27.
Wow, so Ridge just edged it out.
Exactly. By a small margin, but consistently the best across the evaluations. This makes ridge regression the champion for this specific California housing dataset analysis, providing the most accurate predictions among all the models we systematically built and tuned.
So Ridge regression wins the prediction challenge for California housing prices. That's the headline result. But it's not just about that final number, is it? What can we learn by looking inside these winning models, especially Ridge? Does inspecting their learned parameters, the coefficients, offer any additional insights into why they perform so well? Does it tell us anything about the data or the problem?
Absolutely. This is one of those deeper insights you don't often see highlighted just by looking at the final score, but it's incredibly valuable for really understanding your model and the data. Inspecting the learned model coefficients, cofin sklern, and the intercept, is incredibly insightful. While the exact coefficient values can naturally vary slightly across different cross-validation folds or tuning runs, we observed a consistent and powerful pattern when looking at the regularized models. Regularization, particularly ridge regression in this case, helped make the learned weights more uniform and less prone to taking on excessively large or extreme values for certain features. This was especially noticeable for features like avj occupancy, which, if you recall, had shown indications of potential outliers in the raw data during our initial exploration. A simple polynomial model might assign a huge negative or positive weight to such a feature to compensate for those outliers.
But Ridge smoothed that out.
Exactly. Ridge's L2 penalty effectively smoothed that out. This is a direct, observable benefit of regularization. It doesn't just improve predictive performance, it also fundamentally stabilizes the learned parameters. When you peer into the coefficients, Ridge's smoothing effect means it's less likely to put all its faith, so to speak, in one single potentially noisy or outlier-prone feature. It forces the model to distribute the importance more evenly across multiple relevant features. It's a testament to how regularization helps create a model that learns the general underlying patterns, not just memorizes the noise or quirks of the training set, making the final model far more robust and often more interpretable. It's like a wise investor diversifying their portfolio rather than putting all their money on one single volatile stock. Ridge encourages that diversification in the model's reliance on features.
This has been quite a comprehensive journey, really, from that raw, quirky California data all the way to a finely tuned, championship-winning predictive model using ridge regression. For our listeners who followed along, what's the biggest takeaway from this entire deep dive? If there's one overarching lesson they should remember about building effective machine learning models in practice, what would you say it is?
I think the most important lesson, the one that underpins everything we've discussed, is that building effective machine learning models is fundamentally an iterative process. It's rarely, if ever, a one-shot deal where you just plug in some data, run a default model, and magically get a perfect result. That's just not how it works in the real world. Instead, it involves continuous cycles of refinement, a constant feedback loop where each step informs the next. It's about 1. Thorough data exploration. Really taking the time to understand the dataset's characteristics, its quirks, its patterns, its missing pieces, and its potential pitfalls before you even start modeling. 2. Model selection, which means starting with simple baselines to set a realistic performance bar, and then progressively moving to more complex models only as needed, guided by evidence, rather than jumping straight to the most complicated algorithm you can find. 3. Rigorous training. Ensuring your models are actually learning effectively and efficiently from the data using appropriate techniques like pipelines and scaling. 4. Systematic evaluation. Using robust techniques like cross-validation with meaningful metrics to get reliable, unbiased estimates of how well your model actually generalizes. 5. Careful diagnosis. Actively using tools like learning curves and validation curves to pinpoint why your model is performing the way it is it underfitting, overfitting, or hitting that desirable sweet spot? 6. Strategic hyperparameter tuning. Methodically optimizing the model's settings based on those diagnoses, refining its internal configuration to best match the data's complexity and achieve optimal, stable performance. 7. And then, crucially, iterating, reevaluating and refining the model based on these new insights, maybe going back to feature engineering or trying a different model class altogether. This entire deep dive really serves as a practical, comprehensive template for tackling real-world regression problems effectively. It emphasizes that each step informs the next, leading you closer and closer, iteratively, to a truly insightful and powerful predictive model.
We've certainly navigated the intricate world of linear regression today, haven't we? From understanding the quirks and sometimes delightful surprises hidden within our data, to building those pragmatic baselines, exploring powerful polynomial and regularized models, mastering the versatile SGD regressor, and finally, rigorously evaluating and tuning for optimal performance. It's truly a journey that takes curious minds, smart code provided by libraries like Sklearn, and a whole lot of careful thought and systematic effort.
Absolutely. This deep dive really reveals that even for a problem as seemingly straightforward on the surface as predicting house prices, there's a whole world of nuance and strategic decision-making involved. It's in the data preparation, the model choice, and especially in those crucial steps of robust evaluation and strategic tuning. It's all about finding that right balance of complexity and generalizability for your specific data set and your specific problem.
Which I think raises an important final question for you, our listener. After witnessing this systematic approach, this iterative journey to uncovering the best predictive model for California housing, what other real-world datasets or problems in your world, in your work, or your interests could benefit from this very same process? How might these powerful techniques, really understanding data quirks, starting simple, diagnosing issues like underfitting or overfitting, and iteratively refining your approach, apply to a prediction or analysis problem that you're trying to solve, or maybe just curious about? We sincerely hope this deep dive has given you not just some answers about linear regression, but perhaps more importantly, some new questions and new pathways to explore on your own.